Hello everyone, welcome to Lab 3, Black Hole. Here are the equations we'll be using in this lab. The first one is Newton's second law, the momentum principle, where F net equals dp over dt. F net has two different components here. There's the parallel component and the perpendicular component. The parallel component deals with acceleration, such as slowing down and speeding up, and the perpendicular component deals with direction, such as curving. Then we have the momentum formula and the velocity and position update formulas, which we have used in the past couple labs. And lastly, we have the gravitational force equation, which we used multiple times during this lab, not just to find the gravitational force, but also to find a few of the variables that are in the formula. In part 1, we will be using glow script to find the mass of a black hole based on a star's orbit that will be mapped, and then we will be discussing the differences between the parallel and perpendicular components of the net force versus the rate of change of momentum. In part 2, we are pretending that we are a spaceship and we need to find an initial velocity that will allow us to go around the black hole without crashing into it or the planet. And in part 2, we will be doing almost the same thing, except finding an initial velocity that will allow us to orbit the black hole, not just pass by it. So here's what we're working with. The given information, we have the orbital coordinates, we have the mass of the star, and we have change in time. What we're supposed to input is momentum, velocity, net force, and the gravitational force equation solved for mass. And then what we expect to output is the net force and both its parallel and perpendicular components and the mass of the black hole after averaging all the outputs together. So here we have the seed, which will give us the randomized orbital coordinates, and then we have the givens, the gravitational constant, the mass, and the change in time. Here's the actual physics equations. Up top we have momentum, then we have change in velocity and change in momentum, then we're calculating rate of change of momentum, then we're setting that equal to net force, then we're finding the parallel component of dp dt, setting that equal to F net parallel, and then finding the perpendicular component of dp dt, setting that equal to F net perpendicular, and finally we'll find the mass of the black hole by rearranging the gravitational force equation. So this is the output, this is the result. Net force is in orange, the parallel component is in purple, and the perpendicular component is in blue, and this is the star making its orbit around the black hole. As you can see, many different masses are coming out as outputs, and that's because of the calculation loop. So after averaging all these outputs, I found that the mass of the black hole is 1.31 times 10 to the 34th kilograms. What does it all mean? Are the parallel and perpendicular components of net force the same as the parallel and perpendicular components of rate of change of momentum? So as you see in the code for the lab, net force is mathematically equal to the rate of change of momentum. If you remember, like, we literally set them equal to each other. However, the difference is that the rate of change of momentum's components can be solved for by observing the star's conditions like position and velocity. If you noticed, we solved for dp dt first, and then we set it equal to net force. Whereas for net force, it cannot be solved without the mass of the black hole, which is why we had to assign it a value. Part 2 of this lab, we are a ship, and we notice a planet orbiting a black hole, and we decide to land on the planet, and we want to know what initial velocity is needed to take off from the planet and fly around the black hole without crashing into it or the planet. So we're going to be inputting mass, net force, velocity and position, and ship speed, which we have to do guess and check for, and then we expect to get the planet's orbital speed and the ship trajectory. On the right, we use the gravitational force equation to find the net force of the planet because the ship and the black hole are acting on it, and then we also do the same to find the net force of the ship because the planet and the black hole are acting on it, and then we add the velocity and position update formulas for the ship and the planet so that we can mimic their movements. On the left, I just played around with the initial velocity until I found one that allowed the ship to pass by the black hole. Here's what we get as a result. The planet's trajectory is in blue, the ship is purple, and it's passing by the black hole. But what if, instead of just passing by the black hole, I want to orbit the whole black hole? What initial velocity would I need to be able to achieve this? So to find this value, I did trial and error again, but this time I knew to input speeds of lesser magnitude so that the gravitational pull of the black hole would pull the ship in. So on the bottom right of the slide, that is what I put in to get the left picture. And that is all. Thank you for watching.